Okay, so what we're going to cover now is some identities of trigonometry that are going to be very, very important, and we're going to use them quite a bit throughout the semester. And then we will as well use these identities to validate specific trig equations, or we're pretty much going to be proving trig equations. So let's kind of start off by writing out our goal. So our goal here is to work with the fundamental trigonometric identities in order to simplify or prove families of identities. Okay, so before we actually get into the proofs, what I want to talk about first is the fundamental trig identities that we need to know of. So let's start off with the fundamental trig identities, and it's very, very important that you memorize these because you need to know these identities to be able to solve or the proof the equations on the second part. So if we start off, we're going to first start off with our reciprocal identities, which the name should pretty much tell you, because from last section, if you remember, we had some trig functions that were reciprocals of each other. For instance, if you think back to last section, sine and cosecant were reciprocals of each other. So in other words, we're saying sine of theta is equal to 1 over cosecant of theta. It's just, this is one way of writing an equation where I can relate the two. And by the way, I'm also not going to write it the other way around, but also, obviously, if sine of theta is equal to 1 over cosecant theta, then cosecant theta will also equal to 1 over sine theta. Okay, so the other trig, the reciprocal identities we have is cosine of theta is 1 over secant theta. And same thing, we could also say secant of theta is equal to 1 over cosine of theta. So it's true both ways. And then the last pair of reciprocal identities are tangent and cotangent. So for example, we could write tangent of theta as 1 over cotangent of theta. Okay, so the other types of identities we have are the ratio identities, which there's two of them, in which we're basically saying, look, I could write tangent of theta in terms of sine and cosine. So tangent of theta is equal to sine theta over cosine theta. And in fact, we can very simply prove this to verify this, because look, we know from last section that sine of theta, so here's a very simple proof of this. So I'm telling you that tangent of theta is equal to sine of theta over cosine of theta. So here's one way we can prove it. So here's kind of like a small proof of it. If we start with sine of theta over cosine of theta, you'll notice that by definition, what's sine of theta? From last section, we learned that sine of theta is y over r divided by, what's cosine of theta? X over r. And anytime you divide fractions, you could say that's equivalent to y over r times the reciprocal of the denominator, which is r over x. The r's will cancel out, and we have y over x left. And what's y over x? By definition, that's tangent of theta. So notice how we just showed that sine over cosine, or sine theta over cosine theta, is the same thing as tangent of theta. So that's kind of like a quick proof of that. Now, also the other ratio identity we have is that cotangent of theta is cosine of theta over sine of theta. Okay? Now, the last set of identities, which these are also important, are the Pythagorean identities. And there's 3 Pythagorean identities that we need to know. The first one is sine squared theta plus cosine squared theta is equal to 1. Okay, and you can prove this just the same way kind of that the approach I took here. So see if you could show how sine squared theta plus cosine squared theta is equal to 1. Literally, if you write this in terms of y over r, x over r, you combine them, you'll see that you get 1 over 1 pretty much, which gives me 1. Or you get r squared over r squared. Now, the second trig Pythagorean identity is going to be tangent squared theta plus 1 is equal to secant squared theta. And the third Pythagorean identity, and I should make some spacing here, the third Pythagorean identity that we need to know is 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so these are the identities, or these are the important identities that you need to make sure you know, and we are going to use them as we go along, not only in this sections and in future sections to come. So you will work with these quite a bit. Okay, so what we're going to do now is we're going to get into verifying identities using algebra. So what I'm going to do is, as we're verifying these identities using algebra, I'm kind of going to show you some steps that I consider when I go through these proofs. So we're kind of going to be proving these identities. So when asked to verify trig identities, our goal is to work with one side of the equation and manipulate it using the fundamental identities. In order to get it to look like the other side. So, and technically speaking, I mean, if you think about it, when I proved the ratio identity up here, where tangent theta is equal to sine theta over cosine theta, what did I do? I chose one side of the equation, I worked with that, and I got it to look like the other side. Except what's going to happen now is the proofs that we're going to do are going to be a little more involved than the approach I took here. In fact, we're going to use these fundamental trig identities to help us out, okay? So, one comment I want to make is sometimes you might be wondering, hey, which side should I start off with when I'm trying to prove this? Because remember, like we said, we want to pick one side of the equation, use identities, or try to get it to look like the other side. So the comment that I'll make here is that we are usually better off by working with the more complicated looking side. Okay, so basically when you start off with your equation, ask yourself, hey, what's the more complicated looking side? And that's the side we want to prove. Okay, so before we actually do some examples, let me kind of give you some things, some methods to consider. Okay, so here's some steps to consider when verifying identities. So And these have no specific order. I kind of just write them in any order, but usually the first step is sometimes my go-to. Like these proofs sometimes won't be very straightforward or won't be obvious. So I would at least say, look, I'll take this approach. So one thing you could do is write everything in terms of sine theta and cosine theta. Okay, so that's one way. You could say, hey, look, I'm going to write everything in terms of sine and cosine and see where that gets me. The second thing to consider, or the second possible thing you could consider is consider using the Pythagorean identities. If we have, let's say, sine squared theta or a cosine squared theta, etc. Or if we have some trig function squared. Reason being, one comment I want to make is this. Notice that we have, for example, if I'm just going to use one of the Pythagorean identities, this is true for all of them, but I'll use the first one. If sine squared theta plus cosine squared theta equals to 1, we can rewrite this. So this can be rewritten as sine squared theta is equal to 1 minus cosine squared theta. So if you technically think about this, after all, this is an equation. So from here to here, what did I do? I just subtracted cosine squareds from both sides and got this, okay? So in other words, we can use this in different forms, right? So this isn't the only way we could write this, right? We could write it any other way, okay? So what I'm trying to say here is that the same idea can be applied to any Pythagorean identity. Okay? So if you think about it, if you start off with an equation and you have sine squareds, but you know in the end result you want cosine squareds, then obviously you want to use this because you could replace sine squared theta with 1 minus cosine squared. So that's why this is kind of like something nice to consider. That's obviously when you have trig functions that are squared. Okay, so when you see trig functions that are squared, you should think to yourself, hey, it might be a good idea for me to consider using the Pythagorean identities. Okay, now the third thing you could do is if you have quadratics in terms of a single trig function, consider factoring. So one thing that you might notice is, hey, I have the same trig functions, or I have quadratics. I might be able to factor this. So in other words, here's what I'm saying. That is, for instance, if I have something like this, cosine squared theta plus 2 cosine of theta plus 1, when you see something like this, you notice that, hey, this could be factored to, think of this as x squared plus 2x plus 1. However you'd factor that, this would factor the same way. This factors to cosine theta plus 1 times cosine theta plus 1, right? Because cosine squared is the same thing as what? Cosine theta times cosine theta, which notice how this becomes cosine theta plus 1 quantity squared, okay? So, you know, it's things like this. And for example, we could also have another possibility, which is something like tangent squared theta minus 1 is the same thing as, that factors to what? Tangent theta minus 1 times tangent theta plus 1. So what I'm saying is, sometimes look at your equation, you might be able to factor, and if you can factor, great, factor and see if that gets you closer to what you want your end results to be. Okay? So the last kind of step to consider is something like this. If you see fractions, one thing to consider is if I have fractions, I try to combine them into a single fraction. So try to kind of get a common denominator and write them as a single fraction. So one thing you could do is write them as a single fraction by finding the common denominator. Okay, so these are some things for you to consider. Remember, there isn't, just because I number them as 1, 2, 3, 4, it doesn't mean you have to follow them in that order. You don't have to use all methods whenever you're solving. It's just kind of, you could use them in any order you want. It's just what's most appropriate. Okay, so one last comment I want to make before we do some examples and wrap up this section is this. One comment or one thing that gets lost when people are trying to prove these trig identities is they kind of stop looking at what their end result needs to be. And that to me is the most important part. So always, and for me, you'll see when I start going over these, I always do this. So always keep your eye on what we want our final expression to look like. And the reason why, as this will give you a good idea of which fundamental identities to use. Okay, so that's kind of, you'll see as we start doing our examples, which I will do my first example now, I'll always kind of refer to, hey, what's our target? What are we trying to get to? Okay, so let's look at some examples and then that'll wrap up this section. So for example 1, we're going to say verify that sine of theta times cosecant of theta minus sine theta is equal to cosine squared theta. Okay, so the more complicated side obviously is the left side. So I'm going to start with the left side, and my goal is to get it to look like cosine squared. So I boxed this because that's my target, right? That's what I'm looking at. So if I start off with sine theta times cosecant of theta minus sine theta, I look at where I want to go to, and I notice that I want this to turn into cosine. So in other words, one of the first steps was what? Write everything in terms of sine and cosine. So what I could do now is, these signs are okay for now, but the cosecant, I need to write that in terms of sine and cosine. And once I do that, then I'm going to see, well, how could I convert this to cosine squared? So the first thing I want to do is take the first trick out of our playbook, where we said write everything in terms of sine and cosine. And why? Because my end result is in terms of just cosine. So let's not worry about how do we get rid of the sine yet. So then this is fine, this is fine, the only thing is that. And what is it that we know? From our ratio identities, cosecant of theta is the same thing as what? 1 over sine theta. So I'm just using the ratio identity. So from here to here, I'm going to get sine of theta times cosecant is 1 over sine theta minus sine theta. And then what I notice is, well, now what I could do is I could do some simplifying. I could distribute this sine. And what happens when I multiply this sine to the 1 over sine, the signs cancel out. So I get sine theta times 1 over sine theta, that becomes sine theta over sine theta, which is 1, minus, and then sine theta times sine theta, right? I'm just distributing. Sine theta times sine theta is sine squared theta. And now let's look at this. Let's look at the target. I don't want sine squared, I want cosine squared. And see, now this is telling me, why don't I go and look at my Pythagorean identities, because this is in terms of sine squared. Now notice how the first Pythagorean identity is what? If I write it off to the side, I'm just kind of going to write it up here. We know that sine squared theta plus cosine squared theta is equal to 1. And sure enough, look at how nice this is. If I subtract sine squared theta from both sides, what do I get? I get cosine squared theta is equal to 1 minus sine squared theta. Now look, 1 minus sine squared, 1 minus sine squared. So from the Pythagorean identity, what do I know? 1 minus sine squared is the same thing as cosine squared theta. And notice how I started with this side and I showed that it's the same as that side. So the proof is done. I just proved it. Okay? So this was kind of like one example of how we would work with this. So now let's look at our second example. Verify that 1 equals to cotangent squared alpha secant squared alpha minus cotangent squared alpha. Okay, now obviously if we look at this, the more complicated side is the right side. So that's the side I'm going to start with. So I'm going to write cotangent squared alpha secant squared alpha minus cotangent squared alpha, and my target is 1. So here's what I know. The first thing when I look at this, what do you notice that there is? Well, if I look at this, I notice, wait a minute, I can factor, can't I? Because there's cotangent squares on both sides. So if I factor out a cotangent squared alpha, which remember factoring was one of the things I could consider, I get sine squared alpha minus 1, right? Because I factor out a cotangent squared from here, which that's what it gave me. And then I look at this, I say, wait a minute, secant squared alpha minus 1, this looks like one of my Pythagorean identities, doesn't it? And if I look at my Pythagorean identities, is there one with secant squared? There is, isn't there? There's one that says tangent squared alpha plus 1 equals to secant squared alpha. Now remember, whether we write it as theta or alpha, it doesn't matter. So look, how could I get the secant squared alpha minus 1? Well, if I subtract 1 from both sides, then what do I notice I get? I get tangent squared alpha is the same thing as secant squared alpha minus 1. And look at how nice this is. I could now grab the secant squared alpha minus 1 and I could change that to tangent squared. So then I get cotangent squared alpha times tangent squared alpha. And here's the nice part. Look at how beautiful this is. These two are actually reciprocals of each other. Remember the reciprocal identity? And what do we know? We know that tangent is the same thing as 1 over cotangent. So tangent squared would be the same thing as 1 over cotangent squared, right? So just keep that in mind. If tangent is 1 over cotangent, tangent squared is 1 over cotangent squared, tangent to the power of 10 is 1 over cotangent to the power of 10. So why do I like that? Because look, what's my end result? I want to get 1. So if I rewrite this as 1 over cotangent squared, what do I get? Cotangent squared alpha times 1 over cotangent squared alpha. And what do you notice happens to the cotangent squareds? They cancel out, and I got 1. So something like this, where you're like, whoa, this is weird. How am I going to get this to become 1? Which we used our trig identities, and we got to it. Now, keep in mind that these identities that we're verifying, they're not always easy, right? Sometimes you might get lost. Sometimes you might have to go back and try over again. So just be patient with these, because they will get better through time, and the more experienced you become with these, okay? But I think it's safe to say that you will have something to verify, some kind of identity to verify on our exam for chapter 1, okay? So let's look at our third example. So example 3, which says verify that sine of beta minus cosine of beta squared is equal to 1 minus 2 sine of beta cosine of beta. Okay, now from these two, to me the left side looks more complicated. How come? Because I can go ahead and square this out. Okay, so I'm going to make this my target. So this is going to become what? Sine of beta minus cosine of beta squared. And my goal is to square this. Now let's be careful, because when we're squaring this, we need to expand this properly. So I'm just going to write it out like this so we could easily see what's going on. So that sine minus beta cosine beta squared it becomes sine beta minus cosine beta times sine beta minus cosine beta. So if I distribute this out, or I FOIL this out, what do I get? Sine beta times sine beta is sine squared beta. And then what do I have? Sine beta times negative cosine beta, that's minus sine beta cosine beta, and then minus cosine beta times sine beta, that becomes the same thing as minus sine beta cosine beta, and then negative cosine beta times negative cosine beta is plus cosine squared beta. Okay, so let's keep our eye on the target. One thing I know is I could combine these, right? Negative sine beta cosine beta minus sine beta cosine beta, that becomes what? Sine squared beta minus 2 sine beta cosine beta plus cosine squared beta. Okay, now let's take a look at our target. So it's very important to look back at our end result. So what do I want? I want 1 minus 2 sine beta cosine beta. Now what is it that you notice? This guy is already matching up with that. So this guy I don't want to mess with. However, what is this guy missing? We're missing a 1. But then look at what's left over. Sine squared beta plus cosine squared beta. Don't we have a Pythagorean identity that says what? Sine squared beta plus cosine squared beta is 1, right? This is the Pythagorean identity I'm talking about, which was our first Pythagorean identity that I gave you. That. So what could I do? Sine squared beta plus cosine squared beta, we know that that's 1, which is the 1 I was missing, right? So notice how keeping your eye on the target is very, very important, because if I didn't stop here and look how this compares to that or relates to that, then I'd kind of be stuck, right? So technically speaking, I'm kind of cheating, right? Because I'm stopping, I'm saying, hey, what do I want? What don't I want? So I saw this, I'm like, hey, this is cool. I want to keep that because it's the same as that. But these two I don't like. I want these two to become a 1. And you're like, oh, wait a minute. That's my Pythagorean identity. That's just 1. So if I take sine squared beta plus cosine squared beta, I replace it with 1. What does this become? These two become 1, and what am I left with? Minus 2 sine beta cosine beta. And there you have it. We just proved it. Okay, so there's one more example I want to do, but this last example is review of last section. So this is kind of like a review question, which sometimes I like to do this, which is nice because we get to see some stuff from before. Okay, so with that said, let's start this. So if I say given cotangent of alpha is equal to negative 9 over 40 with the terminal side of alpha in quadrant 4. Now we're going to notice why this is important, because we're being told we're in quadrant 4. Find the values of the other 5 trig functions of alpha. Okay, so that's what we're doing. So now, if I start off with this, here's what's important. Let's start off with cotangent of alpha. See, by definition, what is it that we know cotangent is? It's x over y. So based on what we have, x is negative 9, y is 40. Or we have to be careful. This isn't the only way, because negative 9 over 40 is negative 9 over 40. Or we could have what? X could be 9 and y could be negative 40. Because look, if I say this over that and this over that, those two will give you the same result. So the question is, which one of these two is it? And the answer is where? It's in here. Alpha is in quadrant 4. So if we know our angle puts us in quadrant 4, which this is 1, 2, 3, 4, if I pick a point here, what do we know about our x and y values? My x value is positive, my y value is negative. So from these two, which one is has x as positive, y as negative? It's this one. Okay, so this one we don't need. So now, to be able to find the values of the other 5 trig functions of alpha, I also need to find r. And if you remember, r is found by square root of 9 squared times negative 40 squared. So what does that become? Square root of 9 squared is 81. 40 squared is going to be, I believe, 1600. So if I do that and I add 81 to it, I get 1681. And then if I take the square root, this becomes square root of 1681. And if I take the square root, I get 41. So R is 41. So we know that, once again, let's just write this out. X is 9, Y is negative 40, R is 41. Okay, so now let's find the other 5 values. Well, the good news is, or the easy one is what? If cotangent, so let's write this out real quick. We know that cotangent of alpha is negative 9 over 40. Well, then we know that tangent of alpha, which is just the reciprocal of cotangent, that'll be negative 40 over 9. Okay, now let's find sine of alpha. What's sine of alpha? By definition, that's y over r, which is negative 40 over 41. Now remember, last section, the last problem I did, when the angle was given, or we knew what the angle was, we have to write the angle as well. Over here, notice how the angle wasn't given, okay? So there will be a time that we'll actually be able to find the angles ourselves, right? So let's not worry about that yet. But it's important that we always put the angle. If we don't know what the angle is, we have to put the appropriate variable. If we do know what the angle is, we have to put the angle in with it itself, okay? So if sine of alpha is negative 40 over 41, then its reciprocal, which is cosecant of alpha, is negative 41 over 40. And then what else do we have? We have cosine of alpha, which is x over r, which is 9 over 41. And then we have its reciprocal, which is secant of alpha, and that will be 41 over 9. And that takes care of this example. Okay, so this finishes up our section. Now remember, these identities that I proved today, they will take some time for you to grasp and become comfortable with. So if you're looking through the examples that I was doing and you're saying, yeah, I can follow along with what you're doing, but it was kind of difficult for me to kind of see that I would take that approach, don't worry about that. That, just through practice, you're going to get better at it. So obviously I've been doing this long enough where, for me, I look at one of these trig identities that I'm trying to prove, and I have a pretty good idea as to what approach to take. And hopefully you'll get to that point as well through practicing these through your homework. Okay, so once again, if you have questions, do not hesitate to reach out to me.